Okay, we are ready to press on. There will be now another talk which will be by Bjorn Stinner on phase field modeling of free boundary problems. I'll just say that after the questions are, we finish with the questions, it will be 3 o'clock, and then we will take 15 minutes break and resume at 3:15, so you know that. So please, Bjorn.
Yes, thank you very much for the introduction. Pleasure to be here again. So I want to talk, I'm also in computational free boundary problems, but I want to talk about the specific way to approximate, which you can see as a way to approximate free boundary problems. This phase fit methodology. You can see it as a way to smooth the free boundary problems, for that the numerical computations of solutions becomes a bit easier. I can resort then to more the standard methods. We will be using adaptive finite element methods to do so, but you could resort to other techniques as well. People have been using finite difference methods and material science, and I've also seen computations using NURBS and splines, using isogeometric analysis. Yeah, so the computations this way become a bit easier thanks to this smoothing step. Yeah? Right, so I guess I should say a bit about this methodology. And this has given you a rough idea what this is about. I was thinking about using the tumour growth model as well, actually, when it's resorted to this one. This is a more classical application, where also these phase fit models have arguably emerged from and become big with crystal growth. Yeah, so it comes from material science, solidification, crystal growth. Yeah, something like this growth of such crystals can be described by the so-called Stefan problem. It's a classical approach to the Stefan problem, French mathematician. If this set of equations, let me briefly talk through this. The energy plays a role, respectively the heat. So if you cool the system, you will expect some solid parts to grow. So we are solving here the heat equation in the two domains. Omega plus and omega minus stand for this solid part and the liquid part, respectively, in which we solve the heat equation. And then at the interface, latent heat is released at a rate, this latent heat factor, at a rate that is proportional to the velocity of that interface. V nu is the normal velocity of that interface between the solid and the liquid. And this latent heat then is transported away. This is the net flux minus the net flux of the energy into this free boundary. That's the corresponding flux of heat flux. Yeah? Right, so these two equations describe the energy balance of the system. Now you couple the need an additional condition for the free boundary. That's this last one, the so-called Gibbs-Thompson condition. Written it in such a way. So again, the normal velocity features up to some kinetic free factor. On the right hand, we have two terms. So I mentioned that if we cool the system, we would expect the solid part to grow. That's incorporated by this term. Yeah? So if we have a deviation from the melting temperature, then we should see some evolution of the free boundary. But there's also a capillary term. So here I have the surface tension coefficient sigma, and kappa is the curvature. It's the isotropic case here. The equations for the isotropic case here, but you have some capillary term that regularizes interface a bit, but that also gives rise to these typical crystalline structures as we see them in many applications. Yeah, so in this case here, in such case of such crystals, we would here kind of a weighted beam curvature, slightly different term. Would look slightly differently.
Excuse me, so in your second equation, what does the bracket stand for?
It's the jump across the interface. Yeah, so you approach the interface from the two sides, and there's a jump of the two terms. So the two sides are the omega plus and omega minus. Yeah.
Okay, for both, it's a limit expression.
It's a difference between the two.
The difference between the two.
Right. So you can approximate this problem using the phase fit methodology. So it's pretty much. That was the picture you've seen before. So we introduce an order parameter. We may introduce an order parameter phi to distinguish the two phases, but now this doesn't jump at the interface, but we smooth this transition a bit. And so it looks like this. Yeah? So there's a thin layer, for thickness scaling with a small parameter epsilon, over which this phase fit parameter, but also all the other fields then change their values quickly but smoothly. Yeah, and you can achieve this, for instance, if the energy is carrying some sort of energy. Yeah, for instance, if in the limiting problem, it's pretty much what we had in the example before, there's an underlying energy such as the area functional, then you can approximate this, for instance, by such type of a functional, the Ginzburg-Landau energy. It's got a double well potential, and we use a double well to indicate it because it looks like a double well. It's got minima here, -1 and 1. So these states are energetically favorable. Like what we see here, yeah, plus and -1 are energetically favorable. But we want to avoid two drastic jumps between plus and -1. Yeah, so we also have here typically jump that penalizes jumps. Yeah, the upshot then are here energetically or close to equilibrium states are these interfaces. They occur with a thickness that scales with a small epsilon. Yeah, show an example. So here's equation of the two gradient flow of this Ginsburg-Landau energy with some random initial data. And you quickly see that start with random initial values around 0. And quickly these domains form where the phase fit variable is close to plus or -1. And we have these interfaces in between. And it's this long time evolution that we really are interested in. Yeah, so we see that these diffuse layers, they are moving now. And that provides a mean to approximate free boundary problems now. And this is the regime that we are interested in, this long-time regime. I should say we use this, we have the viewpoint that we use these phase-fit methods to approximate free boundary problems. But originally, they were considered as the physically right models, I should say. So, yeah, so these ideas of diffuse interface models was even dated at least to Van der Waals here in the around 1800 something. This is a reprint here of his work, which was in Dutch, so Ronison has translated it. So he was studying the interfaces between gases and liquids. Yeah, and he had the mass density in mind as the order parameter phi that changes its value but doesn't jump across the interface between the gas and the liquid. Yeah, so he had this notion of the diffuse interface already. Yes, it wasn't jumping, but changing its value over thin layer, say some nanometers or whatever. Yeah, but we take this point of view. Yeah, so we use this as a tool to approximate the free boundary problem. Good. So, and in this case, for this specific example seen before, the phase-fit model could look like this. Yeah, so you recognize some of the terms. There's some structure preservation actually. Yeah. So you preserve some of the terms, like here there's again an energy balance. So these two equations are written in one equation. It's smooth in some sense. The phase-fit variable appears here. Yeah. And I also have this Gibbs-Thompson condition here rewritten in terms of this phase-fit variable phi. Yeah. The terms are pretty similar. Also some of the parameters go over in a one-to-one fashion, almost at least. There's some calibration constants coming in. Yeah, but you may believe that the time derivative of the phase fit has something to do with the normal velocity. Yeah, this term here, this is the variation of this Ginsburg-Landau energy with C that gives the curvature term, and here there's the undercooling term. Again, yeah, that drives the evolution of the interface. So, what we're wondering now is whether this process of translating this free boundary problem, sometimes called the sharp interface model, because it's the limit of this problem here is to send the epsilon to 0. But under which conditions we can consider these problems and automatically translate them into a phase-fit model? Can we automate this process somehow? Yeah, is there a generic way, more or less generic way to do so? And then in the sub-step, in the next step, in the second step, can we then just use our more standard methods, adaptive finite elements methods is what we've used. Can we bind then the thus derived phase-fit model formulated as appropriate, and then use some efficient software backends to actually solve this set of equations in order to approximate the free boundary problem? Can we automate this process? Yeah. So I guess I should talk a bit about this relation here, a bit more between these two types of models. Relation, sharp interface model to the phase-fit model. So, if you have a phase-fit model, then identifying the sharp interface model, this problem is rather well posed. Yeah. So if you have a phase-fit model that satisfies, yeah, if you see that if you send the epsilon to 0 by pen and paper calculations or numerical simulations, if you see that somehow that this converges to some limiting problem, as to send the epsilon to 0, then you often have a good chance to identify the equations that govern the limiting model, the sharp interface model. Yeah, you can do that by this by matching suitable asymptotic expansions. So what you would do is you insert some asymptotic expansions in the bulk phases and in the interfacial layers into the governing equations. But in the interfacial layers, you use a stretched coordinate. Now the thickness is so far epsilon. You stretch that to R1. Use the stretch coordinate in the normal direction. Yeah, then you have, that's meaningful. Then you have a chance to go to a limit with any proof points that we have in the interface. Yeah, yeah, and then you plug these two expansions in this interfacial layer and in the bulk into the equation and try to solve. You get boundary conditions for the respective equations by the condition that these two types of expansions have to match up. Yeah, if you approach the interface from the bulk, then the expansions they have to match up with the expansions that you have in the interface and the other way around. And then it's pen and paper calculations that you have to do for this purpose. So we can do that. For instance, let's take again this Einstein equation for which you've seen the simulation. It's the L2 gradient flow of this Ginsburg-Landau energy. That's how it looks like. And we can do this asymptotic analysis and derive, obtain in the limit this governing equation, this geometric equation as a solvability condition. Yeah, it drops out as a solvability condition for that the equations of your expansions are solvable. It's a necessary condition. Yeah, so that has to be satisfied in the limit. Yeah. So it just says here, it's a geometric equation, just says that the normal velocity is equal to the mean curvature. But actually, I've preserved a bit more. Yeah? Notice that this, I mentioned that this here, this is the gradient flow of this Ginsburg-Landau energy. But also this equation here, this geometric equation, is a gradient flow, namely of this area function. Yeah. So this limiting, this limit here has been rigorously assessed. This matching these asymptotic expansions is a rather is a trick to identify the limit, but it's not really rigorous. There's no rigorous analysis, but you can make it rigorous, and some people have done that. But there are also other ways to establish this limit here rigorously. Yeah. So Matisona has used viscosity solution, so in principle, yeah, second order equation, so that can work. Yeah, but beyond that, also Alexander Mielke in a more recent work has looked at these types of problems, and he came up with the notion of an evolutionary gamma limit. This area functional here is the gamma limit of this Ginsburg-Landau energy. Yeah, but he was then thinking towards extending this notion of the gamma limit towards the gradient flows of the respective energies. Yeah, so extending here this limiting process for the energies, extend that to these corresponding gradient flows, and you can make some assertions about that. Particularly this case is covered. Yeah? Okay, so that's this way around, and you can also carry out this analysis then for the other equations that you have in the system here, this matching these asymptotic expansions and deriving the limit. This is rather well posed. The other way around is a rather ill-posed problem. Yeah? Posing any free boundary problem, it's not clear whether there is a corresponding phase fit model at all. And if so, there might be several. The solution is not unique. So you have a good chance to find a phase fit model if there is some energy involved on your free boundary. So as seen in the example before, if you have here this area functional as the energy, then the evolution of the interface might be, at least involves some aspects of the gradient flow dynamics of this functional. Yeah. If you have such a structure there, then you can translate that to a phase fit model. Yeah, you can come up with an energy that approximates this energy and then study the gradient flow of that. You have a chance. But even then, the solution is not unique. You can come up with all sorts of double potentials. So I presented potential that had minimum plus and minus 1, but of course you could put them at any place in space. Yeah, here is potential with minimum and 0 and 1. You could choose that. Yeah, pick any other values. Yeah. Calibration problem. Or you use these obstacle type potentials that Vanessa has used. Yeah, so pick such type of a double potential, yeah, which is infinite outside this range here that you want to find to begin with. Yeah. But still has minima and 0 and 1. Yeah? Then you have to solve variational inequalities.
So you're saying a lot of these choices work, but do all of these choices work? So once I know that my energy functional on the right-hand side approximates my energy functional on the left-hand side, do I know that's
not per se. No, we have to work on that. There's something in addition that comes in. It depends a bit on how the gradient flows are set up. Yeah, you can consider all sorts of gradient flows here. This is an L2 gradient flow. This is also, that's not here actually, but the Einstein equation is the L2 gradient flow of that one. But of course, you can consider all sorts of geometries, and it is not clear whether you converge to the right limit. Yeah? You have to think about the manifolds and the corresponding tangent spaces on which you set up the evolution, the gradient flow dynamics. Yeah? So, for instance, here is it's not that one on the next slide. We have a different type of gradient flow dynamics. Yeah. So this is again an L2 gradient flow, but of this Wilmer energy. It gives this Wilmer flow here, or elastic flow for curves, and you can tend to approximate that one. Yeah, and the end equation we have this term approximating the curvature. So just square that one, integrate it up, and give it a go. Yeah. It's a bit richer actually, the L2 flow of this one. I'm not citing this work here, also Alex. Rets, this and Matthias Röger have done some in-depth investigations of the L2 gradient flow of this energy. We need something that guarantees that you evolve phases in the long term, that these phases of plus and minus one occur. Yeah, but if you have that, then this can work. Yeah, you can approximate the Wilmer flow or something like that. Yeah? Good. So, works if you have an energy. Might sometimes have a chance even if you don't have any energy underlying the system. So here's the example of surface diffusion. Yeah, you can consider that as a fourth order evolution equation, and you can approximate it by, in this case, the degenerate candidate equation. Yeah, so it's kind of a H-1, a weighted H-1 gradient flow now of the Ginzburg-Landau energy. It's a different metric now. Yeah. It's degenerate in that here this mobility coefficient here degenerates if the phi is outside of the range of plus and minus 1. Actually, this is within the range. Outside, you set it to 0. Which I forgot mentioning here. Yeah, and the double potential is a bit peculiar as well. Yeah, involves here another factor that depends on epsilon. So-called logarithmic double potential. Yeah, but you can occasionally also, there's no energy behind that. Yeah, might have a chance.
So we haven't managed to energy behind that. Sorry? How do you know that there's no
okay, I haven't found any energy. I'm not aware of any energy. That's right. Yeah. I haven't managed to anyhow classify these types of cases in which you are able to come up with a phase fit approximation, at least when it comes to the movement of the free boundary. This gives Thomson types conditions or their generalizations, whatever you have. Yeah, so we're still relying on what is in the literature and what can be done, so we haven't got fully our head around it yet. But what does work is when it comes to coupling other equations to these interfacial evolutions, they can be translated into a phase-fit model in a much more generic way. So let's, for instance, have a look again at this energy balance. This is this type of equations that we've seen in the crystal growth problem. Yeah, written a bit more abstractly. If you choose these energies here in the phases as appropriate, then you recover the equations that we've seen before. Yeah, the heat equation in the bulk, and here's this jump condition with a latent heat at the interface. So this equation, this set of equations can be written as in a distributional form like this. Yeah, defined for this E here now, find it to be that distribution. We take the characteristic functions of the two domains, omega plus and omega minus, the time-dependent domains, yeah, together with these internal energy densities, E plus and E minus. Yeah, similarly for the flux, yeah, just study this equation, which is in a distributional form. Yeah, and if you test that against smooth functions, localized in the bulk and at the interface, you recover these two equations again. Yeah, that's equivalent. If E plus and Q are smooth enough, of course, yeah? In their respective domains. So, but now we have got this phase fit variable. So we could go about smoothing here these characteristic functions by means of the phase fit variable. Yeah? So do something like this, for instance. Yeah, if the phi is, if plus and minus 1 correspond to the pure phases, then if phi is 1, then you recover the E plus. If phi is minus 1, you recover the E minus. And in between, you just interpolate linearly here. But you could choose any other interpolation function if you want that. Yeah? Again, there's no uniqueness here, but there's a much more generic way to do so. Similarly for the Q, yeah, and this is the equation that you might want to study in the phase fit model, yeah, coupled to the interface evolution.
May I ask for this distributional form? So I have to think about it given Q and given the omega t, right?
That's right, yeah. That's right. The evolution here is assumed to be given. That's right. Yeah. The gamma is given, and the evolution of the gamma is given.
And I'm looking for E.
It is just an equivalent way to write down the above set of equations.
Yeah.
Here in this case, I mean, this is not closed. This problem is not closed. Yeah, you would have to. Okay. In this case, you would just search for the U with these choices here. Yeah.
I see.
Right.
Okay.
This is not a closed system. I'm just writing down here an equivalent form of the above system, but that's not a Weierstrass problem. You have to close that. Yeah? Some algebraic constraint. But even at that level, at this abstract level, you can translate that into the phase field model, yeah, in this form, yeah. And if you then insert these specific choices, then you recover this very specific equation that we've seen before. Yeah? So this is not done in any ad hoc way, but it's a much more generic way. And you can also do that if you have now equations on the interface that live on the free boundary. And this is done in some much more recent work. So say if you've got a diffusion equation for some species C that is at the interface gamma, at the evolving interface gamma, subject to this diffusion equation, but the interface is evolving, material points are moving in the normal direction, so this object here has a normal time derivative. The time derivative, when you follow these trajectories of material point on the interface, yeah, okay, then it's a conserved equation, yes, C is conserved. So this term here describes the change of the local mass density when you stretch or compress the interface. You know, when you move it against the curvature, the curve will determine if you move that in the normal direction, you locally stretch or compress the interface. Yeah. Right, so that's the equation that we can also approximate. Again, we can write that in a distributional form using here surface delta distribution. Another distribution that if you test that against a function, then you get the integral of the test function over the gamma. Yeah, and this is an equivalent way to write down the above equation. And again, we can here apply the same trick by smoothing now this surface distribution. Use the phase field to smooth that. For instance, like this. Yeah. Just here the double Webb potential is present in the interfacial layer. Just use that one and calibrate that as appropriate. Should scale it 1 over epsilon. Yeah. And then in the limit, if you set the epsilon to 0, and if the interface is given, you have to define the phase field as appropriate, then you approximate the delta gamma. Yeah, and that's the type of equation that you then can consider, which is similar to what we've seen before, yeah? For some aspects, for the logic parts, fields at the interface. Can even make that rigorous. This show that the limit of this problem here is indeed satisfies that equation. If the movement of the interface is known. Not in the case that you couple it with the phase field equation, but if you know what the movement is. Yes, we've done that here in this work of 2008, and then later on consider that again. There's some subsequent work where also other cases where you have some bulk surface coupled problems. I consider that in this case here and here you even get some, assuming higher regularity, you even get some error estimates in terms of epsilon, how fast you converge to the limiting solution. Yeah, and here some nonlinear equations are considered. Yeah, so this can be done in a rigorous way. But crack on. Yeah, it's in the end it's an exercise in some. Okay, we did it for this problem here. What we did is transforming the problem into a reference domain while it's blowing up in the normal direction. Yeah, and then assuming that this delta epsilon here, which is to have finite thickness. So there's a limiting profile towards which this delta epsilon converges in this reference domain. Yeah, and then you use that to set up a weighted Sobolev space, and in the Sobolev space you then go to the limit. You establish some epsilon estimates and come to the limit. Okay. Computations. So in the end we want to solve that computationally, and we've also thought about that. There's this joint work here with Charlie Ennett, Mercer Stiles, and one of his students. Actually, we did, for the computational method, we did not transform to the reference domain, but we did it in the physical space because in the end we had in mind of coupling this to some equation for some phase field variables, yeah, to couple this to other equations. So this is how we've set it up. So we've got this diffuse layer. Again, this is in the case where where the thickness here of this profile is finite. Yeah? So we have a finite layer in which this delta epsilon is present. Yes, so you can imagine this is problematic then. In principle, there's a bulk equation, but it's degenerate in the pure phases. That's what you have to deal with numerically, which probably would also even be a problem if you show some smoother profile, which has some exponentially decaying tails. Even then, this is numerically a problem. So what we came up with was, if you have this thin layer, then extend that a bit and define a numerical computational thin layer by also accounting for vertices that lie outside of the domain, but which have a neighbor that lies inside of the diffuse layer. So in these neighboring points, this delta epsilon is positive, outside it might be 0. So this is the scheme that we then propose. So if, given the data at the previous time step, then this thin layer evolves depending on the velocity field that is given. In this case, we propose to solve this equation here. So what's the KV? So here IH is an interpolation. So what we do here is mass lumping. Now, in vertices that lie outside of this gamma epsilon layer, the corresponding entry in the mass matrix is going to be 0 because of the degeneracy. So you still can solve the system thanks to the contribution from the stiffness matrix. Here we use the interpolation of the delta epsilon because you always have one vertex inside this layer. Here the contribution to the stiffness matrix is not 0. So that saves us. Right, you still have to control this term, this advection term, so we get a constraint on the time step, which is moderate. More interesting would be to preserve mass, at least globally, which means that these two terms turn out to be the same. If you insert chi j equals 1 as a test function, we want that these two terms coincide. And for this purpose, we have to make sure that if you advance from one time step to the next one, that the boundary of this interface does not cross a whole triangle, a whole element. Because then we would lose some information from some points that were associated with some mass here. But if, so roughly speaking, if the time step satisfies such type of a constraint, then this is guaranteed. You preserve the total mass. So I should also say there's some more recent work on a variant of this method. Vanessa, together with Klaus Deckelin, they have looked at that and established some convergence results. Good. In practice, it works in applications. So if you set the epsilon to 0 and h at the same rate, then we obtain a convergence rate that we would expect. Linear convergence in the h1 norm, quadratic in the 2 norm, almost at least. And okay, Vanessa has talked about adaptive mesh refinement. And let me talk about something else. So very recent work. We have been extending these ideas now to networks and clusters. So such type of situations where you now have 3 phases and the geometry is stationary here, but we look at some equations that are present here at these different types of interfaces. So in this case, we would have 3 phase field variables for each of these domains. You have one phase field variable that represents the presence of this domain. And then you can set up the equations at these interfaces by choosing appropriate combinations of these phase field variables to come up with a suitable approximation of the delta distribution. The question is then what happens here at the triple junctions. So in this example, I'm going to show us we have some species diffusing in by some nuclear boundary condition here on this side. It's diffusing in, and the species is then transported through a triple junction to the other interface. On the other side, we've got a natural non-boundary no-flux boundary condition. So the mass is kept on it. So this works. So we've set up the models, in principle it works, but the analysis is still lacking for this type of problems. So you can steer the mass in here on one side and it's diffusing in, and it's then also transported through the triple junction to one of the other interfaces. I'm displaying here is actually here this approximated delta distribution rescaled times the surface concentration. Just between 0 and 1 here. Good. So it can be generalized to multiple phases, to multiple interfaces, these ideas. And actually also to multiple species. So the U or the C could be a vector value field. Good. Good. Software. 10 more minutes. Can we automatize this now? To what extent can we do that? So what we had in mind is a high-level interface to implement these free boundary problems. Just specify what you have at this free boundary problem level, and then this is ideally automatically transformed into a phase-fit model, using these tools that we've seen before, and then which then binds to efficient software backends. Okay. But we don't want this to be a black box. In principle, we should be able to access all the parts in this processing, all the steps in this process. Yeah, so we want that you can have some choice of the potentials that you can go to. You can see, look at the code for the phase-fit model and change that as appropriate. But even also further down, you can change the time stepping routines. You might want to touch on the spatial discretization, change that. Yeah, and even further down, maybe on the non-linear linear algebra solvers, you might want to steer in your favorite precondition or whatever. Yeah, so that should be possible. Yeah, so we don't want to have any black box solver here, as many commercial software provides it. Yes, there might be actually some commercial software for these type of problems. I haven't done a check, but which typically face it then face some limits of it. Yeah, so you can do what the developers had in mind, and for everything beyond, you're typically stuck. So, what are the ingredients that we thought about might be useful? There is this unified form language. It allows to, it's implemented in Python, that allows to variationally formulate partial differential equations. Yeah, in a nice way. It's used by the Phoenix software. But we also use the Dune here as the backend, providing much functionality, even parallel computing would be possible, though we haven't tested that yet. But many solvers, grid managers, etc. Right, so how does it work for this specific example, for the crystal growth example? So here, the equations again, somewhat abstract. So what I would have to specify is now here these E's, the Q's, then in our case the no source terms F, plus some of these terms here, the tau, this is the anisotropic surface energy now. It's kind of a curvature term, but for this anisotropic case now. Yeah, and this driving force here with the undercooling, that's what I have to specify. Plus, of course, I have to say what the domain is, the time domain. Yeah, and initial conditions have to be provided. For the boundary conditions, we have natural boundary conditions, which are the flux conditions that are usually covered by the finite elements that we use. Yeah, so we don't have to touch that. Yeah, and here are the other variables which I'm stating here for completeness. And this data, this specification, now is transformed into the class. We just covered that in the Python class. There we go. Almost the one-to-one fashion. Yeah. So again, specify the domain. There's the mobility coefficient, initial conditions. Okay, so some of the terms are a bit abbreviated here so that it fits onto a slide. So here this non-linearity and the surface energy is a bit abbreviated. Spit is defined elsewhere, and S is this was F, somewhere the forcing term here, undercooling term. Yeah, but also for the flux, this is fairly straightforward. Yeah, for the two domains, we have minus alpha times the gradient of U. It's the flux. U0 because it's set, yeah, so we can account for vector variant fields for U. Yeah, here we only have one scalar field, good enough for vector variant fields. So this class is then translated into the phase-fit model, and then variation is formulated in this UFL, unified form language. I'm not going to show you that for this one because this is already quite messy, and again, it doesn't really fit on two slides. So let's just do that then here for the heat equation for simplicity with discretized in time for the Craig-Nicholson scheme. Yeah, that's better accessible. Right, so what do we define? Okay, we have to define here in the data, the domain, the mesh. We have to define a mesh in the space, a finite element space. Yeah, shortcuts for that, mostly one-liners. We need some finite element function. There was some problem where we had the exact solution underlying, so we initialized it with the exact solution. And this is going to be here the UH here at the previous time step. Yeah, again, it's a finite element function. Yeah. Good, so this is the interesting part, I think. This is the UFL code, in which we code up this problem here. So we need a trial function, that's going to be the UN plus 1. The test function, that's the psi here. We need the time step, delta t, and yeah, for the right-hand side, for the source terms, we need the time, access to the time. And then here this A that we have on the left-hand side, this is covered here in this A, almost in a one-to-one fashion. Yeah, so here's the time, discrete time difference here, first term dotted with a psi, and the last term here star dx. That means that we integrate this term over the domain now. Yeah, fairly straightforward, I think. Simply for the right-hand side here. Yeah, it's just this term here. Coded up. Good. We've got the UFL model, and now Python runs over that. It translates it somehow into a tree, and then translates it into some C++ code, and that then binds to whatever software backend we want to use. But of course, that has to be implemented, yeah, for the specific software backend. You have to bring it into the corresponding. You have to be able to translate it into the corresponding C++ code. Yeah, it works for the student, and of course for Phoenix this works as well. Last bit then, okay, you want to solve this. This is a model, and then we define a scheme using this model. So this is what we want to solve in each time step, A equals B. I found the time step, and then here's the time loop. Yeah, and in each time step, we copy over the UH, the actual UH, to the previous one, just here, that's the solution at the previous time, and then solve the scheme here, A equals B, and store the solution in UH. Voila. That's it. Good. That works. So if we run Python over this, and post process the output data into a movie, and then that's what you get out, yeah, for these specific data. Right.
What kind of time stepping do you use?
It's a fixed one. Yeah, it's a fixed time step.
No, but I mean,
So, for this one,
scheme is just
right. So the default time stepping scheme is just the backward Euler. So you have to solve a nonlinear problem then in each time step by default. But as I said, you can touch the UFL code. You can translate the class, and you can touch the UFL code, and then think about other time stepping routines. Yeah, multi-step methods or whatever.
So this UHN assign UH means just that you have your method and you apply it to the previous step, and out comes the
in
next
this
step.
case, just take this UH is a finite element function. In particular, there's some big space in the memory where you have all the values in the vertices, the dots there. You just copy these over now into the corresponding space for the previous the previous type. So this is just an assignment of copying over. The previous one,
Okay.
yeah. Yeah. This here is the solving step. You know, this is where you solve this equation A equals B. This is the time-consuming bit usually. Yeah?
And another question is, you use Dune and Phoenix. Other people have been advocating Firedrake.
Yeah.
So
I haven't caught up with Firedrake yet. They also use the UFL for sure. And I think the idea behind the Firedrake is also a bit making this more openly, better available to the user. Again, Phoenix suffers a bit from Phoenix. You can translate your problem into the C++, but you better not touch it then afterwards, because loops are unrolled, etc. It's really awful to read. Yeah. It's not, you're not supposed to touch that anymore, but I think with Firedrake, the developers want to revert that a bit. They see the problem that eventually too quickly come to the limits with the software as it is, and want to make it better accessible again. Yeah. But I'm not that familiar with Firedrake.
no.
Yeah.
Okay, thank you.
Right. Almost at the end anyway. Couple of features are covered so far. Yeah, we have played a bit with other time-stepping schemes. Yes, also for the phase field equation. Sometimes has the feeling so every couple of weeks there's a new paper on archive with a new time-stepping scheme for the continuity equation. Mostly coming from the Far East. Yeah, so it would be nice actually to have a tool where you can implement some of these and actually assess them for the efficiency. Yeah, I think it's often lacking. Yeah, in these papers, the comparison with other schemes. Yeah, you can choose different double weld potential or multi-weld potentials for the multi-phase case. I mentioned that one. Yeah, our student has done some computations for that one. Matt Collins, I think I didn't mention him. This joint work with Matt Collins, who's about to submit, and my colleague Andreas Stinner. And anisotropic energies, different types of interpolation functions for the energies and the fluxes, etc., and vector variate bulk fields. We have done a bit with surface fields, but this needs some further configuration. We haven't thought about coupling to fluid flow. It's a big ask. We are working on that. Well, not this student, it will have to be someone else. Higher order geometric equation. It's always been relying on this curvature type flow so far. And this might be of interest as well, hybrid approaches. Yeah, we've done computations where we mixed up different types of tracking and capturing methods. This is something that we were eager to simulate. This is an experimental picture showing lipid phase separation on elastic biomembranes. We are so interested in finding the shape, but the material parameters are influenced by the lipid decomposition. Yeah, so the material parameters, the elastic properties are different here in the red phase to the blue phase. Yeah, so we have done computations where we now use a surface finite element method to relax, to compute the shape, to relax that one, but then use the phase fit method for the phase separation on the interface. So back then it proved very convenient, because that way you can allow for topological changes of this phase separation on the surface. It's one of the benefits of the phase fit methodology. Yeah, so such topological changes are more or less naturally captured. That's more difficult to check to do with when you have tracking methods in general. Yeah.
Do you have conservation something there?
Yes, that's right. Yeah, the enclosed volume is preserved. The total area of the blue and of the red parts are preserved. Yeah,
And
there's some
you
preservation.
maintain that.
It's done with a Lagrange multiplier approach. Yeah. So on top of everything in Newton type method. But again, that would be something that eventually could do at the Python side in the end as well. Yeah, so you don't have to do that on the C++ side. It could be at the higher level. Right, and finally, and this has appeared here in Nature. They made it, I think they made it even on the front cover. So we haven't made that. But at least locally, we've managed to make some impact. This was one of the annual reports here of the Newtons. So we made it onto that one. Okay, with that I want to finish and conclude. Yeah, so we saw this sort of brief introduction to the phase fit method. You've seen discussed the relation between the phase fit and the sharp interface model, and to what extent it can be generically translated, and we've set a couple of bits on this software framework that we are about to develop. Here's some more on also more recent reviews here actually on the phase fit method, if you're interested in that. Yeah, thanks for your attention.
We have time for a few questions. Yeah.
So you start with the model with discontinuities, and then you smoothen it, and then you discretize it again.
Yeah.
So why this extra step? Why can't you directly discretize it?
In principle, for the user, that's what we do, yeah? You avoid you can hide this layer of the smoothing with a phase fit approach. Yeah.
So this is mainly for the analysis then?
I mean, there's much analysis going into the setup of these phase fit equations, and arguably also I didn't show that much on the methods, how we solve them, yeah? But of course, there are many numerical methods. You have to think a bit about it. It's still stiff, these equations. There's a small epsilon coming in. You have to think about those as well, yeah? But there's much methodology available, yeah? So it would be nice if you could make that accessible actually to people, yeah? That they can use these more or less sophisticated methods. Of course, what we also have in mind is the interface. Maybe you've noticed that this high-level interface is set up in such a way that you don't have to use a phase fit method to do so. I could think about front checking methods to approximate these problems as well. It's abstract enough for this purpose. Yeah, but this underlying software here, there's something in Tune. No, I think Phoenix doesn't do that yet. Moving meshes in bulk mesh. Yeah, this is either you can use there are these fitted approaches like Vanessa had it. Yeah, where the surface mesh is the boundary mesh of the bulk mesh. Yeah, so but this has to be set up. Yeah. Or there's the other unfitted approaches where you just have a standard bulk mesh and then the moving surface mesh that is moving through it, but then you have to find if you then integrate anything on the surface, any bulk fields, you have to find the intersections, etc. So I think that software hasn't been there in these underlying backends yet. That's what we would need. fitted case, it might be a bit easier. Then you have the trouble with the remeshing or mesh evolution. Yeah, the mesh call.
Yeah, something else. Do you have some? Have you mostly tried this out on synthetic data, or are you also applying this to the data that you get from various applications? But I mean, yeah. So when you these examples that you're running, where do they come from in a sense?
So the example that the student has considered, these are all examples that are fairly well established in the literature. So we haven't reinvented anything there. There's one, there was this tumor growth example, is the second one, but yeah, we have a multi-phase example and another one. But that's maybe a bit more out of the usual range. The crack propagation problem, where you don't basically only have one phase, but then you have the crack in between. And then you have a restriction on this crack. The crack doesn't move, but only the tip of the crack then moves. So you get a constraint on the tip velocity, which then translates into a constraint of the time derivative of the phase field here. How we go down, climb around. So you again have to solve a variation inequality, but this time for the velocity. Yeah? So these are the types of problems that we have considered, but they all had been, the models had been established in the literature before. So it was more a classification task in this case. Yeah, can we somehow classify these problems, write them in a convenient way, in a generic, so that they can generically be translated.
Okay, shall we take a break? First we thank